Okay, so hi. So we are now in the fifth video of number theory. We're still in the same module, and we are now here in the cornerstone of what we call the principle of mathematical induction. So let's start with the first theorem that we will have today. So um, let's call this theorem 1, shall we say? Theorem 1. Okay, so what does theorem 1 say? So let S, okay, that's a set, be a set of positive integers satisfying the following properties. The following. Shall we put the word following? Okay, first of them is property 1. 1 is in S. Okay, so 1 is in S. Okay, so the integer 1 is in S. Property 2 says that if k is, which is an arbitrary positive integer. Let's fix it. Let's fix this. Positive integer in S. Okay, so k is an arbitrary positive integer in S. So then, if that happens, then we can say that k plus 1 is also in S. So if the following properties hold, then we can say that this S is just equal to all positive integers or to all natural numbers. Okay, so meaning this holds if S is a set of positive integers satisfying the following properties, 1 is in S, and if K, an arbitrary positive integer, is in S, then the next number after it, the K plus 1, is in S. Therefore, this S is just only referring to the natural numbers. Okay, so that's the proof, our theorem 1. Let's prove that. Let's give a proof. Okay, so we're going to prove this by contradiction. Contradiction. Okay, so proof by contradiction. Let's say in our last statement we said that S is in S, so we're going to negate this statement. We suppose that S is not equal to the natural numbers. Okay, so therefore, if S is not natural numbers, we will let something to be um, S prime. Let S prime be all n in the natural numbers, such that these n's, which is in the natural numbers, are not part of S. So this is S prime, right? This is not S. So S prime is for all n in the natural numbers, in the positive integers, but these n's are not part of our S, since S is not equal to your positive integers. So by the well ordering principle, we'll use the WOP. Um, S contains a least element L. Let's call it L prime. Least element L prime. We'll call that L prime because we have the set S prime, so to make it uniform. Okay, so therefore, since L prime is the least element, and we saw in our theorem that 1 is in S, okay, therefore, this L prime, which is the least element in S prime, must be greater than the least element in S, because it is S prime. That is by condition 1. Okay, so sorry, let me fix that letter. Since L prime, okay, is the least element in S prime, is the least element in S prime. So since it's the least element, we can say
It's
that
11
L
o'clock.
prime, okay, we can say that L prime minus 1, okay, is not part of S prime. Okay, why is that? Because L prime is the least. So if we're going to minus something from the least element, well, that it's not the least element, and therefore if this L prime minus 1 is not part of S prime, therefore, okay, so we can say that therefore since L prime minus 1 is not in S prime, so where can it be? Therefore, this L prime minus 1 is in S, because it's not in S prime, so it's in S. So consequently, by condition 2, let's just write by condition 2, I don't know if I can fit that. By condition 2, um, by condition 2, um, we can say that L prime minus 1 plus 1, okay, is, well, L prime minus 1 plus 1 is just equal to L prime, correct? And this is in S, which is a contradiction. This is a contradiction. And also, so this is a contradiction And well, this establishes a theorem. Establishes a theorem. This establishes the, sorry, the theorem. Okay, so this is the end of proof. Let's write it here. Okay, so what happened here? So the thing that happened here is by condition 2, since we know that L prime minus 1 is in S because it's not in S because L prime is already the least element. So by condition 2, going back to condition 2, since L prime minus 1 is in S, we say that if any K is in S, therefore K plus 1 is in S. But L prime minus 1 is in S plus 1 must also be in S because that answers the condition 2. So this is a contradiction because L prime is said to be an element of S prime, not just any ordinary element, but it's the least element of S prime, which turns out that it is an element of S, which is a contradiction. Okay, so this establishes the theorem. Again, let me explain again the proof. Suppose that S suppose that S is not equal to the set of integers, so therefore we let S as S prime as the set of integers, but they are the set of integers specifically which is not in this set S. So we call that S prime. So by the well-ordering principle, this is non-empty. S prime is non-empty, and it's composed of positive integers. So therefore it must have a least element. We call that least element L prime. So by condition 1, we know that S, that 1, which is the least of all the integers there, positive integers rather, the least of all the positive integers is in S. Therefore, we say that L prime, which is in S prime, which is not S, must be greater than 1. Okay, the least element in S prime because one is already in S. That's the least element in S. So therefore, L prime, the least element in S prime, must be greater than 1 because 1 is in S. Okay? So since L prime is the least element in S prime, therefore L prime minus 1 is not in S. So therefore, if L minus 1 is not in S, there are no other choices. If it is not in S, it should be in, or rather, if it is not in S prime, rather, if L prime minus 1 is not in S prime, it has no choice, but um, L prime minus 1 must be in S because it is not an element of S prime. So therefore, it must be an element of S. By condition 2, if any arbitrary positive integer k is in S, therefore, if we're going to add 1 to that k, it should also be in S. But notice here, L prime minus 1 is in S. We said that because L prime is the least. So L prime minus 1 cannot be in S prime. So therefore, it's in S. So L prime minus 1, by condition 2, if we're going to add 1, it must also be in S. But L prime minus 1 plus 1 is equal to L prime, which turns out to be in S, which contradicts to our statement that L prime is the least element in S prime. So this establishes the theorem. I hope you can follow this. Okay, so we also have another theorem which generalizes this one. This is actually the less general one. Um, this theorem you can answer this on your own. This is a proof by exercise. This we mean we will leave the proof as your exercise. This is just generalized theorem. What happens in the generalized theorem? I will not write it anymore since it's quite tedious. The one here, instead of 1, it will become n sub 0. That's the least element in S, n sub 0, meaning it's not 1. And also, um, the condition 2 and the last line is somehow similar with this theorem. It only generalizes it, that it doesn't start with 1, it starts with some arbitrary n sub 0. Okay, so After this theorem, we are ready to welcome to our lessons the principle of mathematical induction. So here we go. Okay, so theorem. Okay, we call this theorem as the principle of mathematical induction. Please forgive my handwriting. Okay, so the principle of mathematical induction, not the best writing in the world. So what does this say? So the theorem states that Pn, okay, let Pn be a statement, be a statement satisfying satisfying the following conditions. Okay, where n is in the integers. Okay, so n is in the integers, and P sub n be a statement satisfying the following conditions. Similar to our theorem 1, first condition states that um, P of n sub 0, P of n sub 0 is true writing that true is quite ASCII now. True for some integer. Oh, quite laggy now. Teacher n sub 0. Okay, okay, so I have changed the the file now. Let's continue this one. That one was really lagging. Maybe a lot of annotations have been made already. So okay, let's continue. So we're now on condition 2. So again, reading this theorem, the principle of mathematical induction rather. Again, the principle of mathematical induction. Let P of n be a statement satisfying the following conditions, where n is in the integers. For the first statement, p of n sub 0 is true for some integer n sub 0. This is the integer, the first integer, and because it's n sub 0, if for condition 2, if p sub k, p of k rather, not sub k, the p of k is true for an arbitrary integer k, which is greater than or equal to n sub 0, then um, p of k plus 1 is also true. Okay, then if these two conditions are met, then we can say that p sub n is true for every integer um, n, which is at least greater than n sub 0. Okay, so let's have the proof of this. The proof will be based from our theorem number 1 that we have had before. So the proof, okay, so let S denote the set of integers which is greater than or equal to n sub 0, for which p of n is true. So since um, p of n sub 0 is true, this n sub 0 is in S. Okay, again, let S denote the set of integers which is greater than or equal to n sub 0. So that is the S for which p sub n is true. So since p sub n sub 0 is true, so therefore we can say that n sub 0 is in S. Okay, so by theorem 1, we're going to use the theorem that we have learned a while ago by theorem 1. Now you remember theorem 1. 1 is in S, and if that's condition 1, and then if k, an arbitrary positive integer, is in S, so therefore k plus 1 is in S. So that is S is equal to the positive integer. So that's our theorem 1. So using this theorem 1 that we have learned, so therefore we can say that S contains all integers all integers greater than or equal to n sub 0. Okay, and then consequently
So consequently, P of n is true for every integer n which is greater than or equal to n sub 0.
And it's greater than or equal to n sub 0. So that ends the proof. My computer is a bit laggy now. I think that's too much mathematics and proofs for today. So I will finish this with the QED. This is enough already. My laptop is telling me to stop proving right now. Okay, so I cannot even write the QED correctly. So let's have it a little bit like that. Okay, so I will be seeing you for the next video of this. Hopefully my laptop will be fixed so that I can prove more mathematical theorems for you guys. Okay, so thanks for watching and see you guys soon. Bye.